So today we're going to talk about something that honestly kept me up at night for a while after I first learned about it. And I don't mean that in a poetic, metaphorical way. I mean I genuinely lay in bed staring at the ceiling thinking about this thing, because once you really understand what we're dealing with here, it becomes almost impossible to wrap your head around, and that feeling, that specific flavour of cosmic vertigo, is exactly what I want to share with you today. We're talking about R136a1. Now, if you've never heard that name before, don't worry. Most people haven't, and honestly that's kind of wild, because this object deserves to be a household name in the same way that black holes are, or the Big Bang is, or even the Sun is. Because R136a1 is not just big, is not just massive, it is, as best as we can tell right now, the single most massive star that we have ever discovered anywhere in the observable universe. And when you start pulling on that thread, when you start really examining what that means, how we found it, how it lives, and how it's going to die, you end up somewhere genuinely strange and wonderful and terrifying. So let's go there. But before we do, I want to set something up that I think is going to make this entire video land differently than it would if I just threw statistics at you. Because that's the thing about stars like R136a1, the numbers are so absurd that they stop feeling real very quickly. And when something stops feeling real, it stops being interesting. So I want to build this slowly. I want to start from a place you already understand, and then walk you step by step into territory that will make your brain do something strange and uncomfortable, in a good way. Let's start with the Sun. Chapter 1. The Cosmic Baseline. Knowing our Sun. You already know the Sun. You've known it your whole life. It rises in the morning, it sets in the evening, it gives you a sunburn if you forget your SPF, and it keeps every living thing on this planet alive. It's the centre of our solar system, and it's been burning for about 4.6 billion years. It will burn for another 5 billion or so before it swells into a red giant and slowly fades out. And in the grand scheme of things, the Sun is just completely, boringly average. Like astronomers literally classify it as a G-type main sequence star, which is the scientific way of saying medium, nothing special, totally ordinary. But here's where we need to pause, because even this boring star is so incomprehensibly large that it already strains our ability to think about it clearly. The Sun's diameter is about 1.4 million kilometers. If you wanted to drive around the Sun's equator in a car going 100 kilometers per hour without stopping, it would take you about 1,600 years. Not days, not weeks, years. The Roman Empire was still going strong 1,600 years ago. That's how long it would take to drive around something we casually refer to as an average star. The Sun contains about 99.86% of all the mass in the solar system. Everything else, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, all the moons, all the asteroids, all the comets, all the dust, all of that together accounts for less than 0.15% of the solar system's total mass. The Sun is basically everything. Everything else is rounding error, and the energy output. The Sun pumps out about 3.8 times 10 to the power of 26 watts. That's 380 yottawatts, which is a word that sounds made up but isn't. To put that in some kind of human context, in a single second, the Sun releases more energy than humanity has consumed in its entire recorded history. Every power plant, every fire, every explosion, every nuclear bomb ever detonated, all of human energy use across all of civilization, is nothing compared to 1 second of the Sun's output. And again, the Sun is average. The Sun is the cosmic equivalent of the middle seat on a regional flight. It's fine. It works. Nobody's excited about it. Now, with that baseline established, with that sense of scale in your head, let's start climbing. Because the universe does not stop at the Sun, not even close. The universe has a ladder that goes up much, much higher than this, and the rungs get progressively more insane the higher you go. Just above our Sun, we have stars that are a few times more massive, then stars that are 10 times more massive, then 100 times, and then things start getting genuinely strange, because at around 150 solar masses, we were supposed to hit a hard ceiling, a physical limit baked into the laws of the universe, a boundary that stars were not supposed to cross, and then we found R136a1. But to understand why finding R136a1 was such a big deal, we need to understand that boundary first, we need to understand why stars are supposed to have a maximum mass at all, because this is one of the most beautiful and slightly unnerving concepts in all of stellar astrophysics, and it's going to completely change the way you think about stars for the rest of your life. Chapter 2. The Eddington Limit. Why stars shouldn't be this big. Let's talk about what a star actually is for a moment, because I think most of us carry a slightly simplified version of this in our heads. A star is, at its most fundamental level, a war. A constant ongoing war between two forces that are trying to do opposite things. On one side, you have gravity. Gravity is always trying to pull the star inward, to compress all the gas and plasma down into a smaller and smaller volume. Gravity wants to collapse the star. Gravity never stops pushing inward, not for a single moment, not for a single millisecond across the entire multi-billion-year life of a star. On the other side, you have radiation pressure. This is the outward force generated by the light and energy produced in the star's core through nuclear fusion. Every photon that gets created down in the core and starts working its way outward is pushing against the stellar material, pushing outward, resisting gravity's inward pull. When these two forces are in balance, when gravity pulling in equals radiation pushing out, you get a stable star. The star neither collapses nor explodes. It just sits there, burning steadily, sometimes for billions of years. This balance is called hydrostatic equilibrium, and it is genuinely one of the most elegant things in nature. Now here's where it gets interesting. As you increase the mass of a star, both forces increase. More mass means more gravity pulling inward, but more mass also means more nuclear fuel, which means a hotter core, which means more energy produced, which means more radiation pressure pushing outward. The question is, do these scale at the same rate? They don't, and this is critical. Gravity scales with mass in a relatively straightforward way, but luminosity, the energy output of a star, and therefore the radiation pressure it produces, scales with mass much more steeply. As stars get more massive, they become disproportionately more luminous. A star that's 10 times more massive than the Sun isn't 10 times brighter, it's more like 10,000 times brighter. The luminosity goes up much faster than the mass. This means that as you keep adding mass to a star, at some point the radiation pressure starts winning. The outward push from the light becomes so intense that it literally starts blowing the outer layers of the star away into space. The star begins losing mass faster than it can retain it. Arthur Eddington, the same Arthur Eddington who confirmed Einstein's general relativity during the 1919 solar eclipse, worked out the mathematics of this in the early 20th century. What he found was that there's a maximum luminosity that any object of a given mass can sustain before radiation pressure overwhelms gravity. This is called the Eddington luminosity, or the Eddington limit. And here's what this implies for stellar masses. If a star gets too massive, it becomes so luminous that it will start blowing itself apart. The radiation from its own core will tear it to pieces, which means that, theoretically, there should be a maximum mass that any star can have. Above that limit, you can't maintain a stable star. The thing just won't hold together. For decades, astronomers put this upper limit at somewhere around 150 solar masses. Some calculations pushed it a little higher, some a little lower, but the rough consensus was that a star significantly more massive than 150 times the Sun simply could not exist in a stable form. The physics wouldn't allow it. It was a hard ceiling baked into the laws of nature. Now, nature does not always read the textbooks, and R136a1 either didn't get the memo or got it, read it and decided to ignore it completely. But before we get to the star itself, we need to talk about where it lives, because the address matters here. The neighbourhood tells you a lot about what kind of object you're going to find, and R136a1 lives in what might be the most extreme address in the entire local group of galaxies. Chapter 3. The Tarantula Nebula, a stellar nursery on steroids. Let me tell you about the Large Magellanic Cloud. The Large Magellanic Cloud is a galaxy. It's a small, irregular galaxy, what astronomers call a satellite galaxy, that orbits our Milky Way at a distance of about 160,000 light-years. On a clear night in the southern hemisphere, you can see it with the naked eye. It looks like a detached piece of the Milky Way, a smudge of light hanging in the southern sky that early European explorers noticed when they started sailing far enough south. The Portuguese and Spanish sailors who encountered it in the 15th and 16th centuries named it after Ferdinand Magellan, the explorer, because it was one of the things that stood out to his crew during their circumnavigation of the globe. The Large Magellanic Cloud is about 14,000 light-years across, which makes it roughly 1/7 the diameter of the Milky Way. It contains a few billion stars, which sounds like a lot but is actually quite small compared to our galaxy's estimated 200 to 400 billion. It's a junior partner, a little satellite swinging around the much larger Milky Way in a slow gravitational dance. But don't let the smaller size fool you, because the Large Magellanic Cloud contains something that the Milky Way cannot match. Something so extreme, so productive, so relentlessly generative of new stars that it makes our own galaxy's star-forming regions look almost quaint by comparison. That something is the Tarantula Nebula. The Tarantula Nebula, officially designated 30 Doradus, is the most active star-forming region in our local group. And I want to be clear about what I mean when I say local group. The local group is the cluster of galaxies that includes the Milky Way, the Andromeda Galaxy, the Large Magellanic Cloud, the Small Magellanic Cloud, and a few dozen other smaller galaxies within a sphere roughly 10 million light-years across. When I say the Tarantula Nebula is the most active star-forming region in the local group, I mean the most extreme stellar nursery in millions of light-years of space. The Tarantula Nebula is about 1,000 light-years across. It contains an enormous amount of gas and dust, raw stellar material, and it is cranking out new stars at an absolutely furious rate. Astronomers estimate that there are hundreds of thousands of stars in and around the Tarantula Nebula, including some of the most massive and luminous stars known anywhere. If the Tarantula Nebula were in the same place relative to Earth as the Orion Nebula, our own galaxy's famous star-forming region, which sits about 1,300 light-years away, the Tarantula would cover an area of sky roughly 60 degrees across. That's about 1/3 of the distance from horizon to zenith. It would be so bright that it would cast shadows on Earth at night. The Orion Nebula, which is already spectacular in binoculars, would look like a faint smudge by comparison. At the heart of the Tarantula Nebula is a dense star cluster called R136. And this is where things start getting truly extreme, because R136 is not just another star cluster. It is one of the densest, most massive stellar clusters known to science, and it is packed with some of the most extreme objects in the universe. The cluster R136, which stands for Radcliffe Catalogue number 136 if you were curious, is only about a few light-years across. Think about that for a moment. In a space smaller than the distance between the Sun and the nearest star system to us, R136 packs in hundreds of massive luminous extreme stars. The stellar density there is extraordinary. If you were on a hypothetical planet inside that cluster, the night sky would be almost incomprehensibly bright. There would be multiple stars visible that would appear nearly as bright as the full moon. Some would be even brighter. The night would never really get dark, and inside this already extreme cluster, at or very near the centre, is R136a1. Finding it, though, was not easy. In fact, the story of how we came to even know it exists is a really beautiful example of how science works. Incremental, competitive, sometimes messy, always honest with itself eventually. And it involves one of the most important tools in modern astronomy. Chapter 4. Discovery. How do you find the biggest star? Here's a problem. If you want to study the most extreme stars in the universe, you need to look at extremely crowded, extremely distant regions of space. The most massive stars don't form in isolation. They form in clusters, surrounded by enormous amounts of dust and gas and many other stars. And R136 is not just crowded, it's extraordinarily dense. Trying to resolve individual stars inside a cluster like R136 from Earth is like trying to read individual words on a page from several miles away. For a long time, astronomers couldn't do it at all. When you looked at R136 through even the best ground-based telescopes, the cluster appeared as a single bright, fuzzy blob. Astronomers suspected there were multiple stars in there, but they couldn't separate them. The individual stars all blurred together into one smear of light. In the early 1980s, using a technique called speckle imaging, which exploits rapid atmospheric distortions to reconstruct sharper images, astronomers were able to start pulling apart some of the stars in R136's core. They began to resolve that what looked like one object was actually many, but the resolution was still limited, and the individual components they were identifying were still themselves unresolved clusters of multiple stars. Then the Hubble Space Telescope changed everything. The Hubble, launched in 1990, sits above Earth's atmosphere, which means no atmospheric blurring, no turbulence, no distortion. And when astronomers pointed Hubble at R136 in the early 1990s, for the first time they were able to see individual stars in the cluster's dense core. The smear of light broke apart into distinct points, and what they saw was extraordinary. The stars at the centre of R136 were not just very massive, they were in a completely different category from anything seen before. The first detailed Hubble observations in the 1990s identified several stars in the cluster's core that appeared to be shockingly luminous, far more luminous than anything that was supposed to exist under the theoretical limits. But even Hubble, as transformative as it was, has its limitations. The very centre of R136 was still difficult to resolve completely. Several of the brightest, most extreme objects in the cluster's core were being blended together in the observations, making it difficult to say with confidence which component was responsible for how much light. The real breakthrough came in 2010. A team of astronomers led by Paul Crowther at the University of Sheffield used Hubble data, specifically data from an instrument called the Space Telescope Imaging Spectrograph, combined with data from a ground-based telescope in Chile that used a technique called adaptive optics to dramatically sharpen its images. Adaptive optics works by measuring atmospheric distortions in real time using a reference star or a laser guide star, and then correcting for those distortions hundreds of times per second using a deformable mirror. It's one of the most impressive technological achievements in observational astronomy. By combining Hubble's resolution with the adaptive optics ground data, Crowther's team was able to do something that hadn't been possible before. They were able to separate the light from the individual stars in R136's extremely dense core, and then analyze the spectrum of each individual star to determine its properties, its temperature, its luminosity, its mass. And what they found for one particular star, the one we now call R136a1, was genuinely shocking. The estimated mass of R136a1 came back at around 265 to 320 solar masses, not 150, not 200. 265 to 320 times the mass of the Sun. This wasn't just a little bit above the supposed limit, this was almost double the supposed limit. The paper that Crowther's team published in 2010 in the journal Monthly Notices of the Royal Astronomical Society caused an immediate stir in the astronomy community because the implications were enormous. Either the Eddington limit was wrong, or something had happened with this star that no one had fully accounted for, or the mass estimates were somehow mistaken. Now it's worth saying here, because science requires us to say it, that measuring the mass of a star at 160,000 light-years distance, embedded in one of the densest star clusters known, is genuinely hard. There are significant uncertainties in the measurement, and over the years since 2010, subsequent studies have revised the estimated mass of R136a1 somewhat downward, with some analyses suggesting a current mass of around 200 to 250 solar masses, and a possible initial mass, and when the star first formed, of somewhere between 250 and 320 solar masses. And even at the lower end of these estimates, even if R136a1 is only 200 times the mass of the Sun, it is still, by a very significant margin, the most massive star ever confirmed. The next few competitors on the list are also found in R136, stars called R136a2 and R136a3, and they come in at estimated masses somewhere in the range of 150 to 200 solar masses. Still extraordinary, still beyond what the textbook said should exist, but they are firmly second and third. R136a1 stands alone, so how does something like this form? How do you build a star that shouldn't be able to exist? The answer is fascinating, and it involves a process that's only possible under very specific extreme conditions. Chapter 5. Formation. Building the impossible. Normal stars form through a process called accretion. A cloud of gas and dust in space begins to collapse under its own gravity. As it collapses, it heats up, and eventually the centre of the collapsing cloud becomes dense and hot enough to ignite nuclear fusion. You have a star. The remaining material around the central protostar either gets blown away by the radiation from the newly ignited star, gets pulled in and added to the star's mass, or settles into a disk that can eventually form planets. This process works beautifully for stars up to a certain mass, but for very massive stars pushing toward and beyond that 150 solar mass region, there's a problem. The moment a massive protostar ignites, it becomes so luminous that its radiation starts blowing away the surrounding gas and dust before all of it can be accreted. The feedback from the newly formed star interferes with the formation of the star itself. It's like trying to fill a balloon that has a hole in it. You're adding gas, but gas is escaping at the same time. For a long time, this was seen as a fundamental reason why stars much above 150 solar masses shouldn't form. The radiation feedback would cut off the gas supply before the star could grow that large. The physics seemed to set a natural upper limit on stellar mass during formation, consistent with the Eddington-based predictions, but nature found a workaround. Several, actually. One possibility that theorists explored was stellar collisions and mergers. In an extremely dense star cluster, and R136's core is about as dense as it gets, massive stars don't have much personal space. They're packed tightly together, moving relatively quickly, and the probability of close encounters or even direct collisions between massive stars is actually non-negligible. If two massive stars collide and merge, a process called a stellar merger, you can produce a single object more massive than either progenitor. Do this enough times, in a cluster dense enough, over a long enough period, and you could conceivably build something as massive as R136a1. Another possibility involves a more efficient accretion process. Some theoretical models suggest that under the right conditions, specifically if gas is accreted in a disk or through dense filaments that are partially shielded from the central star's radiation, the feedback problem can be partially overcome, and stars can grow much more massive than the simple, spherically symmetric models would predict. Recent work suggests that both processes may contribute. The extremely dense environment of a cluster like R136 may allow star formation to proceed differently than it does in more typical environments. The cluster's overall gravity may funnel gas toward the center more efficiently, and stellar mergers may indeed be happening, possibly even ongoing during the earliest phases of R136's history. There's also the metallicity factor, and this one is really important. Metallicity, in astronomy, refers to the abundance of elements heavier than hydrogen and helium in a star. Astronomers call everything heavier than helium a metal, regardless of whether it's actually a metal in the chemical sense. So oxygen, carbon, nitrogen, neon, silicon, iron, all of these are metals to an astronomer. The Large Magellanic Cloud has a lower metallicity than our galaxy, roughly half of the Milky Way's abundance of heavy elements. Why does this matter for stellar mass? Because the mass loss rate of a massive star, how quickly it blows material off its surface, is strongly dependent on metallicity. Heavy elements in a star's atmosphere are very efficient at absorbing photons from the star's radiation and being pushed outward, carrying mass with them as they go. This is called radiation-driven stellar winds. More heavy elements means more efficient absorption of radiation, means stronger stellar winds, means more mass loss. In a lower metallicity environment like the Large Magellanic Cloud, stellar winds are weaker. A massive star loses mass more slowly. This means that a massive star forming in the Large Magellanic Cloud can retain more of its initial mass over its lifetime, and may be able to grow larger during formation because the radiation feedback is slightly less effective at blowing away the infalling gas. This is one of the reasons why R136, located in the LMC, might be home to the most extreme stars known. The conditions there, the extraordinary density of the cluster, the large gas supply in the surrounding Tarantula Nebula, and the lower metallicity may conspire to produce stars that simply cannot form in most other environments. But here's something that makes all of this even more interesting. R136a1 is not a static object. It's not sitting there comfortably, burning away, holding steady. It is an object in violent, constant, dramatic turmoil. It is, in almost every meaningful sense, barely holding itself together. And understanding how it lives, what its day-to-day existence is like, if you can even call it that, is where the story gets truly spectacular. Chapter 6. Living at the Edge. The daily reality of R136a1. Let's talk about what kind of star R136a1 actually is, because it's a specific type that most people have never heard of. And this type, the Wolf-Rayet star, is one of the most extreme classes of object in stellar astronomy. Wolf-Rayet stars were first identified in 1867 by two French astronomers, Charles Wolf and Georges Rayet, when they noticed a set of stars with very unusual spectra. Normal stars show absorption lines in their spectra, dark lines where specific elements in the stellar atmosphere absorb specific wavelengths of light. Wolf-Rayet stars show emission lines instead, bright lines where elements in an expanding shell of gas around the star are emitting light. This was strange and new, and it indicated that these stars were surrounded by rapidly expanding luminous shells of gas. We now understand what Wolf-Rayet stars are. They are massive stars that have lost, or are actively losing, their outer hydrogen envelopes through incredibly powerful stellar winds. The stellar wind from a Wolf-Rayet star is not like the gentle solar wind from our Sun. The Sun's solar wind is a trickle. The solar wind from a Wolf-Rayet star is a hurricane that makes the word hurricane seem inadequate. R136a1 is classified as a Wolf-Rayet star of the WN type, specifically a hydrogen-rich WN star, which means it still retains some hydrogen in its outer layers, unlike more evolved Wolf-Rayet stars that have shed all of their hydrogen. This suggests that R136a1, despite being only a few million years old, is already in an advanced stage of evolution by stellar standards. It's burning through its fuel at an absolutely catastrophic rate. And when I say catastrophic, I mean it literally. R136a1 has a surface temperature of approximately 46,000 Kelvin. For comparison, the Sun's surface is about 5,778 Kelvin, so R136a1's surface is roughly 8 times hotter than the Sun's. This is so hot that the peak of its radiation output is not in visible light, it's in the ultraviolet. The star is pumping out an extraordinary amount of ultraviolet radiation, which is one of the reasons it's so destructive to the surrounding nebula. The luminosity of R136a1, its total energy output, is estimated at between 6 and 9 million times the luminosity of the Sun. Let's take the conservative estimate and say 6 million solar luminosities. The Sun puts out 3.8 times 10 to the 26 watts. R136a1 puts out 6 million times that. In every single second, R136a1 releases more energy than the Sun releases in several days. In a year, R136a1 releases as much energy as the Sun would release in about 6 million years. If you replace the Sun with R136a1, Earth would be a scorched rock in minutes. The habitable zone, the distance from the star where liquid water could theoretically exist on a planet's surface, would be far beyond Pluto's orbit. Maybe 10 or 20 times further out than Pluto, our entire solar system, out to the very edge of the Kuiper Belt, would be baked clean of life. The stellar wind from R136a1 is moving at speeds of thousands of kilometers per second. The Sun loses about 100 millionth of its mass per year to the solar wind, an incredibly tiny fraction. R136a1 loses about a millionth of its mass per year. That sounds like a small number too, but remember, R136a1 contains somewhere around 200 to 300 solar masses of material. A millionth of that per year is equivalent to losing roughly the mass of several Earths per year. Every year, thousands of Earth masses of stellar material are blasted away from R136a1's surface and flung out into the surrounding nebula. This is why massive Wolf-Rayet stars exist on such short timescales. They are burning themselves alive. They are so luminous, so energetically active, so feverish in their nuclear burning that they consume themselves at a pace that would seem almost violent if we could watch it in real time. The age of R136a1 is estimated at about 1 to 2 million years. In stellar terms, this is newborn. The Sun is 4.6 billion years old. R136a1 is somewhere between 1 and 2 million years old, and it's already in an advanced state, already classified as a Wolf-Rayet star, already shedding mass at an extraordinary rate, already well into the final stages of its short and spectacular life. By the time the Sun reaches the age that R136a1 is now, it will still be in the earliest, most stable phase of its existence, changing almost imperceptibly. By the time R136a1 reaches an age comparable to the Sun's current age, 4.6 billion years, it will have been dead and gone for 4.598 billion years. Its entire life will fit into a sliver of time that is almost trivially short on cosmic scales. And when it dies, When R136a1 finally exhausts its fuel and collapses, what happens is one of the most spectacular and mysterious events in stellar astrophysics. An event so extreme that it makes a standard supernova look like a firecracker. It involves a class of explosions so powerful that they weren't even considered theoretically possible until relatively recently. And the endpoint, what gets left behind, might be one of the most exotic objects in the universe. But that's for another part of this story. What I want to do right now, before we move on, is just sit with the numbers for a moment, because I don't want them to blur past you. I want them to actually land. R136a1 has a mass somewhere between 200 and 300 times the mass of the Sun. The Sun, which is so massive it accounts for 99.86% of our entire solar system, and R136a1 is 200 to 300 of those. The radius of R136a1 is estimated at somewhere around 30 to 40 solar radii, which means that if you put R136a1 where the Sun is, its surface would extend out beyond the orbit of Mercury and possibly approach Venus. Our inner solar system, the rocky planets, would be inside the star. The luminosity is 6 to 9 million times the Sun. More energy every second than the Sun releases in multiple days. The stellar wind is carrying away thousands of Earth masses of material every year, and in approximately 2 to 5 million years, an instant in cosmic time, it will be gone. It will detonate in one of the most violent events the universe has to offer, seed the surrounding nebula with heavy elements it has synthesized in its core, and leave behind something extraordinary. This is R136a1, and we're only just getting started. End of part 1. Approximately 4,800 words, continuing in part 2. Wait, I need to meet the requirement of 6,000 words. Let me continue part 1 with an additional section. Chapter 7. The Numbers Game. Putting scale in perspective. I want to do something a little different here, because I think the numbers we've been throwing around have started to do that thing where they become abstract, where they're just big numbers, and big numbers are hard to feel, so I want to try a few different ways to make R136a1 feel real. Not just intellectually comprehended, but actually viscerally understood. Let's start with mass. R136a1 contains somewhere around 200 to 300 times the mass of the Sun. The Sun's mass is about 2 times 10 to the power of 30 kilograms. That's a 2 followed by 30 zeros in kilograms. If you took R136a1 and somehow broke it apart into Earth-sized pieces, you'd get roughly 60 million Earths. 60 million planets the size of ours. That's how much stuff is packed into this one star. Another way to think about it. The mass of R136a1 is so large that even Jupiter, which is 318 times the mass of Earth and contains more mass than all the other planets in the solar system combined, would need to be scaled up by a factor of about 200,000 to match R136a1. You would need 200,000 Jupiters to equal one R136a1. Now let's try volume. R136a1's radius is about 30 to 40 times the Sun's radius. Volume scales with the cube of the radius. So if R136a1's radius is 35 times the Sun's, its volume is 35 cubed times the Sun's volume. That's about 42,000 times the Sun's volume. 42,000 suns would fit inside R136a1. 42,000. If you lined up suns side by side across R136a1's diameter, you'd fit about 70 of them. It is, in terms of sheer physical size, one of the largest stars known as well as the most massive. Though interestingly, it's not the largest star by radius. There are giant and supergiant stars with significantly larger radii, though they're much less massive. But we'll come back to that distinction in a moment. Now let's try light. R136a1 is approximately 160,000 light-years away. This means that the light we see from R136a1 today left the star 160,000 years ago. 160,000 years ago, modern humans were alive. Homo sapiens had existed as a species for perhaps 100,000 years or more at that point. Stone tools were in use. Cave paintings would be made by our ancestors within the next several tens of thousands of years. The agricultural revolution was still more than 150,000 years in the future. The light that carries our current information about R136a1 left, that star in the deep Stone Age of humanity. When we observe R136a1 today, we are not seeing it as it is now. We are seeing a 160,000-year-old photograph. This has a slightly unsettling implication. We don't actually know the current state of R136a1. If something dramatic happened to R136a1 in the last 160,000 years, if it exploded, if it collapsed, if it underwent some major transformation, we wouldn't know yet. The light carrying that information is still on its way to us. It's out there, right now, travelling toward us at the speed of light, and it will arrive at some point in the future. It's entirely possible, not likely given the estimated remaining lifetime of the star, but theoretically possible, that R136a1 no longer exists, that it has already met its end in a spectacular explosion, and the light from that explosion is currently somewhere in the space between the Large Magellanic Cloud and the Milky Way, still travelling toward us. Maybe that light is 10,000 years away from us, maybe 50,000, maybe it will arrive tomorrow. We genuinely don't know. And now let's talk about luminosity one more time, but in a different way. If you stood on a hypothetical planet at the same distance from R136a1 as Earth is from the Sun, about 150 million kilometers away, the amount of radiation hitting you would be roughly 6 million times what we receive from the Sun. The Sun already delivers about 1,360 watts per square meter to Earth's upper atmosphere. 6 million times, that is about 8 billion watts per square meter. That is not a number that has any meaning in terms of survival. At that distance from R136a1, there is no concept of surviving. The radiation would not just kill you, it would tear apart molecules, it would ionize atoms, it would sterilize the planet as thoroughly as anything short of a nuclear explosion. The habitable zone, the region where temperatures might allow liquid water, would be somewhere around 4,000 to 5,000 astronomical units from R136a1. For reference, 1 astronomical unit is the distance from the Earth to the Sun. Pluto orbits at about 40 astronomical units. The outer edge of the Kuiper belt is perhaps 50 astronomical units. The hypothetical Oort cloud begins at roughly 2,000 astronomical units, so the habitable zone around R136a1 would be beyond the Kuiper belt, somewhere out in the depths of what, around our Sun, is the beginning of the far outer solar system. Any planet sitting in the habitable zone around R136a1 would also be bombarded by extraordinary levels of ultraviolet and X-ray radiation, intense stellar winds that would strip away atmospheres and gravitational perturbations from the dense star cluster surrounding R136a1. The environment near R136a1 is not just hostile to life, it is comprehensively, redundantly, and thoroughly hostile to life in a way that makes the most extreme environments on Earth seem like pleasant vacation destinations. And yet, and this is something I find genuinely beautiful, R136a1 is not a destroyer in the long run. Not really, because all of that mass it's shedding, all of that stellar wind material it's blasting into the surrounding nebula, all of those heavy elements it's producing in its core through nuclear fusion, all of that stuff becomes the raw material for the next generation of stars, and planets, and possibly life. The carbon in your body was made in the interior of stars that lived and died before the Sun was born. The oxygen you're breathing was forged in stellar cores. The iron in your blood was synthesized in the final moments of a stellar explosion billions of years ago. Stars like R136a1, with their extraordinary mass and their brief violent lives, are among the most productive factories of heavy elements in the universe. They produce elements like carbon, oxygen, neon, silicon and iron in enormous quantities, and then, when they die, scatter those elements across enormous volumes of space. Without stars like R136a1, without massive stars that live fast, die young, and seed the universe with heavy elements, the universe would be a much simpler, much less interesting place. There would be no rocky planets, no complex chemistry, no life. So R136a1, for all its violence, for all its indifference to anything we might recognize as hospitable, is in a very real sense a contributor to the story that leads to us. Every atom in your body has a history that goes back to stars, and the most massive stars have contributed the most to that inventory. That's the end of part 1. We've covered the baseline, the physics, the discovery, the formation, and the daily reality of the most massive star ever found. In part 2, we're going to talk about what comes next, how R136a1 will die, what it might leave behind, and what that tells us about the universe we live in. So we've established what R136a1 is. We've walked through the physics of why it shouldn't exist, how we found it anyway, how it formed in one of the most extreme environments in the local group, and what its day-to-day existence looks like, which is essentially a controlled explosion that has been going on for about 1 million years and is slowly becoming less controlled with every passing century. But here's the thing, the life of R136a1 is only half the story, maybe less than half, because what this star does when it dies, how it ends, what it leaves behind, what it contributes to the universe in its final moments, that might actually be the most important and most spectacular part of the whole narrative. And to get there, we need to understand something about how stars die in general, because the death of a star like R136a1 is not just a bigger version of a regular stellar death. It is something qualitatively different, something that sits at the boundary of what we understand and what we're still figuring out. And honestly, that boundary is one of my favourite places in all of science, because that's where things get genuinely strange. That's where the equations start doing unexpected things, where the physics starts producing results that feel almost fictional, and where the gap between what we know and what we're trying to figure out becomes not a source of frustration, but a source of genuine electric excitement. So, let's start climbing. Chapter 8. How Stars Die. A Ladder of Violence. Let me walk you through the death sequences of stars, starting from the bottom and working our way up, because the way a star dies is almost entirely determined by how massive it was when it was born, and as we climb the mass ladder, the deaths get progressively more dramatic, more violent, and more interesting. This isn't just background context. Understanding this ladder is essential to appreciating why R136a1's death is in a category so far above the rest that it almost needs its own taxonomy. Start with the small ones. Stars like red dwarfs, stars less than about half the mass of the Sun, are the most common type of star in the universe. They burn their fuel so slowly and so efficiently that they can live for tens of billions, even hundreds of billions of years. The universe is only about 13.8 billion years old, which means that not a single red dwarf has ever died of old age yet. They're all still going. When they do eventually exhaust their fuel, billions or trillions of years from now, they'll simply cool and fade. No explosion, no dramatic finale, no last gasp fireworks. They'll become cold, dark cinders called black dwarfs. Quiet endings for quiet stars. The universe will be a much darker, much cooler, much lonelier place when the last red dwarf finally goes out and there will be nobody left to notice. Then there are stars like the Sun, medium-sized main sequence G-type stars. When they exhaust the hydrogen in their cores in about 5 billion years, they'll begin fusing hydrogen in a shell around the inert helium core, which causes the outer layers to expand enormously, transforming the Sun into a red giant. It will swell to perhaps 100 times its current radius, potentially engulfing Mercury, Venus, and possibly Earth. After the red giant phase, helium fusion ignites in the core, burning helium into carbon and oxygen. When that fuel is exhausted too, the outer layers drift outward in a beautiful expanding cloud called a planetary nebula. The name is a historical misnomer, having nothing to do with planets, but the objects themselves are genuinely gorgeous, and the remaining core a dense ball of carbon and oxygen roughly the size of Earth, but containing about half the Sun's mass is left behind. This is a white dwarf, incredibly hot when it first forms, but gradually cooling over billions of years into a cold, dark remnant. No explosion. Quiet, like the red dwarf. A gentle fade rather than a dramatic exit. Now we start climbing into serious territory. Stars between about 8 and 20 solar masses, stars significantly more massive than the Sun but still far below the extreme end of the mass scale, follow a much more violent path. They burn through their fuel much faster, living lives of tens of millions of years rather than billions. They are, in the cosmic sense, mayflies, brilliant and brief. When they exhaust their fuel, the sequence of events accelerates dramatically. The core, which has been building up heavier and heavier elements through successive stages of nuclear burning, hydrogen to helium, helium to carbon, carbon to neon, neon to oxygen, oxygen to silicon, silicon to iron, finally reaches iron, and iron is where nuclear fusion stops being energetically favourable. You can't get energy out of fusing iron with anything. Iron is the ash at the bottom of the stellar furnace. when the iron core reaches a critical mass, about 1.4 times the mass of the Sun, a value known as the Chandrasekhar limit, the electrons that were holding up the core against gravity can no longer do their job. The core collapses almost instantaneously, in less than a second, from a size roughly comparable to Earth to a size roughly comparable to a city. The outer layers of the star, which were happily fusing lighter elements up until that moment, suddenly find the floor has dropped out from under them. They fall inward, accelerating toward the newly collapsed core, and then they bounce. The shockwave from that bounce tears through the star and blows the entire outer envelope into space in a colossal explosion called a core collapse supernova. A core collapse supernova is one of the most energetic events in the universe on human timescales. In the space of a few seconds, it releases more energy than the Sun will emit in its entire 10 billion year lifetime. Most of that energy, about 99% of it, comes out as neutrinos, those ghostly, nearly massless particles that barely interact with anything. They pour through the collapsing star almost as if it weren't there, carrying the bulk of the explosion's energy out into space. The remaining 1% comes out as light and kinetic energy, and that 1% is enough to briefly outshine the entire galaxy the explosion occurs in. A single star, in its death throes, momentarily emits more visible light than hundreds of billions of other stars combined. This is what supernovae look like from a distance, and it's extraordinary. What gets left behind depends on the mass of the collapsing core. For stars in the 8 to 20 solar mass range, the collapsed core typically forms a neutron star. An object about 20 kilometers across, the size of a mid-sized city, but containing 1.5 to 2 solar masses of material. The density is staggering. A single teaspoon of neutron star material would weigh about 1 billion tons. The atoms in a neutron star are crushed so completely that electrons and protons merge into neutrons, creating a kind of quantum mechanical state of matter that doesn't exist anywhere else in the universe. Some neutron stars spin hundreds of times per second, emitting beams of radio waves that sweep across space like a cosmic lighthouse. These are pulsars, and they were so strange when first discovered that the astronomers who found them briefly, half seriously, labelled the signal LGM-1 for little green men. They genuinely weren't sure what else could produce something so regular. For more massive stars, those above perhaps 20 to 25 solar masses, the collapsing core is too heavy for even neutron degeneracy pressure to stop. The neutron star itself collapses further, past any known stable state, into a black hole, a region of space-time so warped by gravity that not even light can escape once it crosses the event horizon. The supernova explosion may or may not happen fully in these cases. Some massive stars may collapse almost silently, without the dramatic explosion, while others produce both the supernova and the black hole. The details are still being worked out. But the endpoint is the most extreme object in the known universe, so that's the general picture. Small stars fade out, medium stars puff up and leave white dwarfs, massive stars explode in supernovae and leave neutron stars or black holes. The more massive the star, the more violent the death, the more extreme the remnant. But here's where R136a1 breaks the ladder, completely. Because R136a1 is not just more massive than the stars we've been talking about. It's so far above the standard massive star range that it enters a completely different regime, one where the standard core collapse supernova story may not apply at all, where something else, something fundamentally different and even more dramatic, may happen instead. Something that was considered purely theoretical for decades before we started finding stars massive enough to actually undergo it. Chapter 9. The Pair Instability Supernova. When physics gets weird. To understand what might happen when R136a1 dies, we need to talk about a phenomenon called pair instability. And this is one of those concepts in astrophysics that sounds almost too strange to be real, but is completely rigorously grounded in well-understood physics. The strangeness comes not from any exotic new theory, but from taking ordinary quantum mechanics and thermodynamics and applying them to conditions so extreme that ordinary intuitions break down completely. In the cores of ordinary massive stars, as they approach the end of their lives, the temperature climbs to extraordinary heights. We're talking temperatures of billions of degrees, so extreme that the photons buzzing around in the core carry enormous individual energies, far into the gamma ray portion of the electromagnetic spectrum. And at these temperatures, something remarkable starts happening that has no analogue in everyday experience. High-energy gamma-ray photons can spontaneously convert into pairs of particles, an electron and its antimatter counterpart, a positron. This process is called electron-positron pair production, and it's a direct consequence of Einstein's most famous equation, E equals mc squared. Given enough energy, you can create matter and antimatter out of pure light. The photon converts into the mass of an electron and a positron, plus whatever kinetic energy is left over. This is not hypothetical or exotic. It has been demonstrated in particle accelerators here on Earth, but in the core of a star near the end of its life, it happens at a scale that has enormous consequences for the star's structural stability. Here's the critical thing. Those gamma-ray photons that are being converted into electron-positron pairs were doing a job. They were part of the radiation field that was contributing to the outward pressure holding the star up against gravity. When they get converted into particles, they stop being radiation. They stop pushing outward. The radiation pressure that was helping to support the star against its own gravity drops. Suddenly, the balance that kept the star stable is disturbed. Gravity gets the upper hand, at least momentarily. The core starts to contract, and here's where the feedback loop begins. Contracting the core heats it up further. Higher temperatures mean more energetic photons. More energetic photons mean more pair production happening per unit time. More pair production means more radiation pressure lost, which means gravity wins more, which means more contraction, which means more heating. You can see where this is going. It's a runaway instability, a positive feedback loop that causes the core to collapse far more rapidly than anything in a standard stellar evolution scenario. But then something dramatic happens. The rapid compression of the core doesn't just heat it up, it causes a thermonuclear runaway. The temperature spikes so fast and so dramatically that enormous quantities of nuclear fuel, oxygen, neon, silicon, everything that hasn't already been burned, ignites almost simultaneously. We're talking about a thermonuclear explosion happening inside the core of an already collapsing star. The energy released in this thermonuclear runaway is so extreme that it doesn't just slow the collapse. It doesn't just halt it. It reverses it completely, with enormous violence. The explosion propagates outward through the entire star with so much energy that it can unbind every single layer of it, blowing all of the stellar material, core and all, every atom, into space. No remnant, no neutron star, no black hole, no cold cinder slowly cooling in space, nothing left behind at the center. The star is entirely and completely destroyed, converted into a rapidly expanding cloud of gas and newly synthesized heavy elements, moving outward at speeds of tens of thousands of kilometers per second, several percent of the speed of light. This is a pair instability supernova, and it is, without any close competition, the most energetic type of stellar explosion we know of. While a standard core collapse supernova releases on the order of 10 to the 44 joules of energy in light and kinetic energy, which is already almost impossible to contextualize, a pair instability supernova can release 10 to 100 times more energy than that. We're talking about 10 to the 45 joules or more of energy released in a single explosion. The total luminosity at peak can exceed that of an ordinary supernova by a factor of 10, 100, sometimes more. The star doesn't just explode, it annihilates itself in a thermonuclear detonation so complete that it erases itself from existence. Let me give you a sense of what that means in absolute terms. The energy released in a pair instability supernova is roughly equivalent to converting several solar masses of matter directly into energy via E equals mc squared. A few solar masses of matter. If you took the entire Earth, all of it, the oceans, the mantle, the core, and converted it entirely into energy, you'd get about 5 times 10 to the 41 joules. A pair instability supernova releases something like 10,000 times that amount. This is the most energetic thing a single star can do. Pair instability supernovae are predicted to occur for stars with helium core masses above a certain threshold, roughly corresponding to initial stellar masses between about 130 and 250 solar masses, depending on metallicity and other factors. Below this range, you get standard core collapse supernovae. Above this range, for the most massive stars imaginable, something even more extreme may happen, something we'll get to in a moment. R136a1, with its estimated initial mass of 250 to 320 solar masses, sits right at the top of this range, possibly above it, which means its fate is genuinely uncertain in the most scientifically interesting way possible. There is also an intermediate possibility that theorists have worked out in considerable detail, called pulsational pair instability, for stars whose core masses sit just below the threshold for a complete pair instability disruption. The thermonuclear runaway triggered by pair production may not be quite enough to unbind the entire star in one shot. Instead, it blows off a large fraction of the outer envelope, releasing an enormous amount of energy in the process, an event that itself looks like a spectacular supernova from the outside, but the remaining core survives. Then the pair instability sets in again as the core continues to evolve. Another explosion, another portion of the envelope ejected. This could happen multiple times, in a series of violent pulses separated by years or decades or centuries, each one releasing a supernova's worth of energy, before the final collapse of whatever core material remains. The observational signature of a pulsational pair instability event would be extraordinary. Astronomers would see a star undergo what looks like multiple supernovae in rapid succession, or sometimes a series of dramatic brightening events separated by longer quiescent periods. We have actually observed objects that may be examples of this phenomenon. The famous supernova imposter Eta Carinae in our own Milky Way underwent a dramatic brightening event in the 1840s called the Great Eruption that released energy comparable to a supernova while the star survived. While Eta Carinae is not currently thought to be in the pulsational pair instability regime, it gives us a qualitative sense of what these repeated violent mass ejection events can look like. Chapter 10. The Black Hole. Question: what gets left behind? Now, I want to return to something I mentioned briefly, because it has implications that go far beyond R136a1 itself. For stars at the very top of the mass distribution, those above approximately 250 solar masses at the upper end of theoretical estimates, the pair instability mechanism may not fully destroy all of the stellar material. The thermonuclear energy released might be enough to eject the outer envelope spectacularly, but the innermost core, under such extreme gravitational compression, might collapse directly into a black hole before the explosion can completely unbind everything. This scenario, called direct collapse, would produce what theorists call an intermediate mass black hole. And this is where things get interesting from a cosmological perspective, not just a stellar one. Black holes come in a range of sizes, and the size distribution is not continuous or uniform. Stellar mass black holes, the ones created by ordinary supernovae, typically have masses between about 5 and 50 solar masses, though recent gravitational wave detections have pushed the upper end of this range somewhat higher. Supermassive black holes, the behemoths that sit at the centres of most large galaxies, range from millions to billions of solar masses. Sagittarius. A star, the black hole at the centre of our Milky Way, is about 4 million solar masses. M87 star, the black hole famously imaged by the Event Horizon Telescope collaboration in 2019, is about 6.5 billion solar masses. These are almost incomprehensibly large objects. In between stellar mass and supermassive lies a territory that has, until very recently, been frustratingly empty from an observational standpoint. Intermediate mass black holes, objects with masses between roughly 100 and 100,000 solar masses, were predicted by theory but very hard to find in practice. They don't accrete material in the same obvious luminous way that active supermassive black holes do. They're too small to dominate the dynamics of an entire galaxy, but too large to be produced by typical stellar evolution scenarios. They were, for a long time, the missing middle of the black hole mass spectrum. If R136a1 undergoes direct collapse, if its core collapses into a black hole without a complete explosive disruption, the resulting object could have a mass of perhaps 50 to 100 solar masses or more, depending on how much of the envelope is ejected and how much falls into the nascent black hole. That would make it one of the most massive stellar remnants produced by a single star, a genuine intermediate mass black hole seed. And here's where the cosmological implications become profound. We genuinely do not fully understand how the supermassive black holes at the centres of galaxies grew to their current sizes. The universe is 13.8 billion years old, but we have already observed quasars actively feeding supermassive black holes, with masses of billions of solar masses at redshifts, corresponding to just a few 100 million years after the Big Bang. Growing a black hole to 1 billion solar masses in just a few hundred million years is extremely difficult to achieve through gradual accretion alone, even if you start with a black hole of stellar mass and it accretes at the maximum possible rate continuously. You need a head start. You need seeds that are already significantly massive. Intermediate mass black holes produced by the deaths of very massive stars like R136a1, or even more massive population 3 stars in the early universe, could be exactly those seeds. The most massive stars in the early universe, forming in metal-poor gas clouds and potentially growing to hundreds or thousands of solar masses before collapsing, could have produced intermediate mass black holes that then grew, through accretion and mergers, into the supermassive black holes we observe today. The black holes at the centres of galaxies, the most massive gravitational engines in the universe, may be the evolutionary descendants of stars not entirely unlike R136a1. There is a direct line, possibly, from the birth of a star to the formation of the most massive objects in the universe. R136a1 represents a link in that chain, an object that bridges the world of stellar astrophysics and the world of cosmology. Its death may produce one of the seeds from which cosmological structure ultimately grows. Chapter 11. R136a1 and its siblings. The extreme star ecosystem. One of the things I find most compelling about R136a1 is that it doesn't exist in isolation. It's not some lone freak of nature sitting by itself in empty space, a single anomaly surrounded by ordinary stars. It is embedded in one of the richest, most extreme stellar ecosystems ever documented, the core of the R136 cluster, itself sitting at the heart of the Tarantula Nebula, one of the most active star-forming regions in the local group. And when you look at the neighbourhood, you realise that R136a1 is the most extreme example of a broader phenomenon. The R136 cluster contains dozens of stars that would each individually be among the most massive and remarkable ever discovered if they weren't being somewhat overshadowed, quite literally, by R136a1 itself, R136a2 and R136a3. The two nearest competitors in terms of mass within the cluster, each have estimated masses somewhere in the range of 150 to 200 solar masses. To put that in perspective, these stars, which are essentially R136a1's immediate neighbours and siblings, are themselves beyond what the pre-2010 theoretical consensus said should be possible. They would be world record holders in any other context. They are extraordinary objects in their own right. But they are firmly second and third in the R136 hierarchy, and the gap between them and R136a1 is significant. Other stars in the cluster, designated R136a4, R136a5, R136b, R136c, form a broader family of extreme objects, all sharing the same remarkable birthplace, all having formed from the same reservoir of gas within a span of perhaps 1 million years or so. They are siblings, in a cosmological sense, born together in the most productive stellar nursery in our galactic neighbourhood. Beyond R136 itself, the broader Tarantula Nebula contains hundreds of O-type stars, the hottest and most massive category in the standard stellar spectral classification scheme. O-type stars have surface temperatures above 30,000 Kelvin, masses typically above 16 solar masses, and are so luminous that they appear blue-white to the human eye. Most O-type stars would already be considered extraordinary objects in a more typical environment. In the Tarantula Nebula, they're practically unremarkable background characters. The combined radiation output from all of these massive stars is doing something on a vast scale to the surrounding gas and dust. The ultraviolet photons they produce are so energetic that they ionize the hydrogen and helium in the surrounding nebula across an enormous volume, hundreds of light years in every direction. This creates one of the largest HII regions of ionized hydrogen, known in the local group. The brilliant crimson glow of the Tarantula Nebula in astronomical photographs is the light of hydrogen atoms, being constantly ionized by the radiation from the cluster's massive stars, and then recombining and re-emitting photons at characteristic wavelengths. R136a1 and its siblings are quite literally making the nebula shine. But there's something even more interesting happening here. The stellar winds from R136a1 and the other massive stars in R136 are not just flowing outward passively, they're interacting with the surrounding gas in structured, dynamic ways. When a powerful stellar wind runs into relatively stationary gas, it creates a shocked region, a bubble of hot, tenuous gas surrounded by a dense shell of compressed material. As the wind from R136a1 pushes outward, it sweeps up the surrounding gas into an expanding shell that can stretch for tens of light years in every direction. Multiple stellar winds from multiple massive stars interact with each other, creating complex overlapping bubble structures within the nebula. And here is one of the more beautiful ironies in all of astrophysics: those compressed shells of gas, those dense walls of material being pushed outward by the winds from R136a1 and its neighbours, are themselves becoming the sites of new star formation. The compression of the gas as the wind-driven shell sweeps through it raises the local density above the threshold needed for gravitational collapse, triggering the formation of new stars on the shell's outer edge. R136a1, through its violent stellar wind, is actively creating the conditions for new generations of stars to be born. So R136a1 is not just destroying its surroundings, it is simultaneously and paradoxically nurturing them. Every solar mass of material it sheds through its stellar wind, every photon it sends into the surrounding nebula is contributing, in a messy, indirect but genuinely real way, to the star formation process in the broader Tarantula Nebula. When R136a1 finally explodes, the shockwave from that explosion will compress further gas, trigger further star formation, and scatter the heavy elements synthesized in its core throughout the surrounding nebula. Those heavy elements will eventually be incorporated into new stars, new planets, and, if conditions are right, possibly the biochemistry of living things billions of years from now. The violence of the most massive star in the universe is, in the long run, generative. Chapter 12. What R136a1 tells us about the universe. Here's the deeper question that R136a1 forces us to confront. Not just, how did this star form, or how will it die? But what does its existence tell us about the universe we live in? What does finding a star that, by our best theoretical understanding, should not exist, tell us about the laws of nature and the limits of our models? The answer, I think, is genuinely important, and it comes in several parts that build on each other. First, R136a1 tells us that the upper limit on stellar mass, the Eddington-based prediction of around 150 solar masses, was not a hard fundamental law of nature etched into the fabric of reality. It was a limit based on idealized, simplified assumptions that don't always hold in the messiness of the real universe. In the turbulent, gas-rich, densely packed environment of a young massive star cluster like R136, the rules are bent by circumstances. Stars can form through mergers and complex accretion processes that circumvent the radiation feedback mechanisms that were supposed to prevent their formation. The universe found a workaround, as it so often does, and that workaround produced something extraordinary. This is a recurring theme in the history of science. We observe nature, we build models. The models make predictions, including predictions about what cannot exist, what is forbidden, what lies beyond some hard boundary. And then nature shows us something that sits comfortably on the wrong side of that boundary, forcing us to go back, examine our assumptions, find what we missed, and emerge with a better, more nuanced, more complete picture of how things actually work. R136a1 is a spectacular ongoing example of this process. It didn't just push at the boundary, it drove a vehicle through it at high speed. Second, R136a1 tells us something important about the early universe. The very first stars, population 3 stars, formed from gas clouds composed almost entirely of hydrogen and helium, with essentially no heavier elements at all. No oxygen, no carbon, no iron, no silicon. Nothing heavier than helium in any significant quantity. The metallicity of these primordial gas clouds was effectively zero, and in a zero metallicity environment, stellar winds are far weaker, because there are no heavy elements to efficiently absorb radiation and carry mass away from the stellar surface. A massive population 3 star would lose far less mass during its lifetime than a comparable star with modern metallicity. It would retain more of its initial mass, and it could potentially grow much larger during formation, because the radiation feedback from the growing protostar would be less effective at blowing away infalling gas. Theoretical models of population 3 stars suggest they may have been enormously massive, potentially several hundred, possibly even 1,000 or more solar masses in some extreme cases. They were the universe's first light, and they were likely the most extreme stellar population that has ever existed. We cannot observe them directly. They formed more than 13 billion years ago, in the first few 100 million years after the Big Bang, and even the James Webb Space Telescope, which has pushed further back in cosmic time than any previous observatory, cannot resolve individual population 3 stars. We see their collective imprint on the universe's chemical history, on the reionization of the intergalactic medium, but we cannot point a telescope at one and study it the way we study R136a1. But R136a1, forming in the lower metallicity environment of the Large Magellanic Cloud, may be our best available analogue, our closest accessible approximation of the conditions that produced those first stars. It's not a perfect analogue. Its metallicity is perhaps half that of the Milky Way, not zero, but the principles are the same: lower metallicity, weaker winds, higher potential maximum mass. By studying R136a1 and understanding its formation and evolution, we gain insight into the physical processes that governed the first generation of stars. We're using a nearby extreme object to build the tools needed to understand a distant, inaccessible one. Third, R136a1 challenges and refines our models of stellar evolution for massive stars in ways that matter enormously across all of astrophysics. These models are not just academic exercises. They are fundamental to our understanding of how galaxies form and evolve, how the universe became chemically enriched with heavy elements, where the gravitational wave sources detected by LIGO and Virgo come from, and how the large-scale structure of the universe developed. Get the massive star models wrong, and errors propagate outward through cascading dependencies into almost every other area of astrophysics. Get them right, and everything becomes more precise, more coherent, more connected. Every time R136a1 surprises us, and it has surprised us multiple times, from the initial shock of its discovery, to the ongoing debates about its precise mass, to the questions about its formation mechanism, it gives us data we can use to calibrate and improve those models. It is not just spectacular for its own sake, it is scientifically productive in a fundamental way that ripples outward through the discipline. Chapter 13. Observing the Unobservable, the Technical Frontier. Let me bring you back to something practical for a moment, because I think it's worth appreciating just how technically demanding it is to study a star like R136a1. We've been talking about its properties, its mass, its luminosity, its temperature, its stellar wind, as if we measured them in some fairly direct, straightforward way. But the reality is enormously more complex and technically demanding than that, and the story of how we actually extract this information is itself a remarkable achievement of human ingenuity and technological sophistication. R136a1 is 160,000 light-years away. At that distance, it subtends an angle on the sky so tiny that even the most powerful telescopes cannot resolve it as a disk. It appears as a point of light, just like every other star. We cannot see its surface. We cannot image its atmosphere. We cannot watch its wind flowing outward. We can only analyze the light it sends us, an extraordinarily information-rich signal, but one that requires sophisticated tools and careful interpretation to decode. The primary tool is spectroscopy. When R136a1's light passes through a spectrograph, it is spread out into its component wavelengths, creating a spectrum that stretches from the ultraviolet through the visible and into the infrared. This spectrum is not just a rainbow of colours, it is a richly detailed record of everything that has happened to that light on its journey from the star's surface to our detector. It contains the fingerprints of every element present in the star's atmosphere and wind. It records the temperature and density of the gas it passed through. It encodes information about the velocity of the stellar wind through Doppler shifts. It tells us the star's surface temperature through the overall shape of the continuum emission. The wavelengths at which emission lines appear identify specific elements: hydrogen, helium, nitrogen, carbon, oxygen, and their relative strengths tell us the abundances of those elements in the stellar wind. The width of the emission lines, broadened by the Doppler effect, tells us the terminal wind velocity, how fast the material is moving by the time it has been accelerated away from the stellar surface. The ratio of certain line strengths gives us the temperature and ionization conditions in the wind. Each piece of information is extracted through detailed modelling, comparing observed spectra to the predictions of sophisticated radiative transfer codes that model the flow of radiation through a stellar wind. But none of this is simple when you're trying to study a star embedded in one of the densest stellar clusters known. The spectra of neighbouring stars, some of them nearly as extreme as R136a1 itself, contaminate your observations unless you can spatially separate the light from each star with sufficient angular resolution. The diffuse emission from the surrounding Tarantula Nebula adds its own spectral signatures. The interstellar dust between us and R136a1 absorbs light preferentially at shorter wavelengths, reddening the observed spectrum in a way that has to be carefully modelled and corrected. Every measurement comes with systematic uncertainties that have to be rigorously quantified and honestly reported. Determining the mass of R136a1 is particularly challenging because, as best we can tell, R136a1 is not in a close binary system with another star. If it were, the solution would be comparatively straightforward. Orbital dynamics give you masses directly through Kepler's laws, but for an apparently single star at 160,000 light-years, mass has to be inferred indirectly by comparing observed properties to the predictions of stellar models. This introduces model-dependent uncertainties that are not always easy to quantify. Different teams using different model assumptions have obtained somewhat different mass estimates, and the discrepancies between these estimates reflect genuine scientific uncertainty rather than careless work. This is why the mass estimates for R136a1 have evolved over time. The 2010 Crowther et al.'s paper, that first characterized the star in detail, estimated an initial mass of 265 to 320 solar masses, and a current mass of around 265 solar masses. Subsequent analyses using updated atmospheric models and improved spectral data have generally suggested somewhat lower, but still extraordinary masses. Current mass estimates typically fall in the range of 200 to 250 solar masses, with initial masses of 250 to 320 solar masses. These revisions are not embarrassments. They're exactly what science is supposed to do. Each new analysis incorporates better data or better models or both, and the picture gradually sharpens. What's genuinely exciting is that the observational tools available for studying objects like R136a1 are advancing rapidly and dramatically. The James Webb Space Telescope, with its extraordinary infrared sensitivity and its location above Earth's atmosphere, has already delivered remarkable science on dense stellar clusters and star-forming regions. Its infrared capabilities allow it to peer through dust that blocks optical telescopes and to detect the signatures of stellar populations and individual extreme stars with unprecedented sensitivity. The extremely large telescope, currently under construction on Cerro Armazones in the Atacama Desert of Chile, will, when completed, have a primary mirror 39 meters across. It will be the largest optical and near-infrared telescope ever built by an enormous margin. Its adaptive optics systems will be so powerful that it can achieve angular resolutions comparable to or exceeding the Hubble Space Telescope while collecting vastly more light. This combination of resolution and light-collecting power will allow astronomers to study individual stars in R136's dense core with a level of detail that is currently simply not achievable. Mass estimates will improve. Orbital dynamics of potential close companions may become detectable. The physical properties of R136a1 and its siblings will be constrained with a precision that we can only anticipate right now. Chapter 14. The Competition. Are there bigger stars hiding out there? Now here's a question I want to sit with for a moment, because I think it's one of the most interesting and genuinely open questions in this whole field, and it's one that often gets glossed over in favour of simply asserting R136a1's record-breaking status. Is R136a1 actually the most massive star in the observable universe? Or is it just the most massive star we've found and characterized so far? This is not a trivial distinction, and the honest answer is that we genuinely don't know. The observable universe contains somewhere on the order of 2 × 10 to the 23rd stars, a number so large it's effectively meaningless to human intuition. 200 billion trillion stars. Our ability to study individual stars in detail drops off extremely rapidly with distance. Beyond a few kiloparsecs, a few tens of thousands of light-years, we can study individual stars only if they're extremely luminous. At the distance of the Large Magellanic Cloud, 160,000 light-years, we can study the most extreme stars but struggle to resolve dense clusters. In external galaxies millions of light-years away, individual stars become essentially impossible to study in detail without special techniques. So when we say R136a1 is the most massive star known, we should be clear-eyed that this means, of all stars that have been adequately characterized in terms of their mass, R136a1 sits at the top. The sample we're drawing from is genuinely tiny compared to the total stellar population of the universe. Are there regions in more distant galaxies, in denser or more extreme star-forming environments, that harbour stars more massive than R136a1? It would be surprising if there weren't. The Tarantula Nebula is extraordinary, arguably the most extreme star-forming environment in the local group, but the universe is vast and star-forming regions with even more extreme properties may exist in starburst galaxies, in the dense nuclear star clusters at the centres of actively star-forming galaxies, in the early universe when gas densities and star formation rates were globally much higher. Gravitational lensing is beginning to give us windows into individual stars in galaxies that would otherwise be completely unresolvable. When a massive foreground galaxy or galaxy cluster acts as a gravitational lens, it can magnify background galaxies by factors of hundreds or even thousands, temporarily bringing individual stars in those background galaxies to within the detection threshold of our best telescopes. The Hubble Space Telescope and the James Webb Space Telescope have both exploited this technique to detect individual luminous stars in galaxies billions of light-years away. Some of these stars appear to be extraordinarily luminous, comparable to, or potentially exceeding, the luminosity of R136a1. These are early results, and the characterization of individual stars through gravitational lensing is still a young field with significant uncertainties. But the technique is maturing rapidly, and it promises to extend the reach of stellar astrophysics to distances that were previously completely inaccessible. The theoretical upper limit on stellar mass, whatever it actually is, remains genuinely uncertain. Before 2010, the consensus was around 150 solar masses. R136a1 shattered that. Current theoretical work suggests that under optimal conditions, very low metallicity, extremely dense cluster environments, significant stellar merging, stars of perhaps 500 to 1,000 solar masses might be achievable, at least in principle. Population 3 stars in the early universe may have exceeded even these limits. We don't know where the true ceiling is, and that uncertainty, that genuine, honest scientific uncertainty, is not a weakness. It is an invitation. It is the universe saying, there is more here than you've found yet. Keep looking. The next discovery may be the most important one, and somewhere in the data that already exists, or in the observations that will be made in the next decade, the next R136a1 might already be waiting to be found. R136a1, the biggest star in the entire universe. Part 3 of 3. We've come a long way together in this video. We started with the Sun, that comfortable, familiar, average star at the centre of our solar system, and we used it as a baseline to climb into increasingly extreme territory. We talked about the physics that was supposed to prevent stars like R136a1 from existing. We talked about how we found it anyway, embedded in one of the densest and most productive stellar nurseries in the local group. We talked about how it lives, barely, violently, magnificently, and we talked about how it might die, in an explosion so complete and so ferocious that it would erase itself entirely from existence, leaving nothing behind but an expanding cloud of newly forged heavy elements, and possibly the seed of a black hole that could eventually grow into something that organizes an entire galaxy. Now I want to do something slightly different in this final part. I want to zoom out. I want to take everything we've learned about R136a1 and use it as a lens, a way of seeing the universe more clearly than we could before we knew this object existed. Because the best scientific discoveries don't just add facts to a list, they change the way you see everything else. They shift your perspective in ways that are permanent and irreversible, and R136a1 I think does that. If you really internalize what this star is, what it represents, what it implies about the universe we live in, you come out the other side seeing things differently. So let's zoom out, and then let's zoom back in, one final time, to something personal and strange and genuinely moving that I've been saving for the end. Chapter 15. the mass function, why giants are rare. Before we zoom out to the cosmic scale, I want to address something that might have been nagging at you throughout this entire video. If R136a1 is so extraordinary, if stars this massive can exist and can form under the right conditions, why don't we see more of them? Why is the universe not full of R136a1 class objects? Why is this star so rare that it took us until 2010 to characterize it properly? The answer lies in something called the initial mass function, and it is one of the most important empirical relationships in all of stellar astronomy. The IMF, as it's abbreviated, describes the distribution of stellar masses at birth. How many stars of each mass are produced when a star-forming region creates a new population of stars? And the distribution is deeply, profoundly skewed toward the low end. The initial mass function was first worked out by Edwin Salpeter in 1955, and while it has been refined and extended in the decades since, the fundamental insight remains unchanged. For every one star born with a mass above 10 solar masses, you get roughly 1,000 stars born with masses comparable to the Sun or lower. For every star born above 50 solar masses, you might get tens of thousands of lower mass stars. And for every star born at R136a1's mass range, above 200 solar masses, you might be talking about millions or even hundreds of millions of lower mass stars produced in the same star-forming event. The IMF follows what mathematicians call a power law. As you go to higher and higher masses, the number of stars born at that mass drops steeply, roughly as the mass raised to the power of negative 2.35 in Salpeter's original formulation. This means that doubling the mass produces not half as many stars but roughly 5 times fewer. The drop-off is steep and relentless. Why does nature produce stars this way? Why are low-mass stars so much more common than high-mass stars? The answer is connected to the very physics of star formation that we discussed earlier. When a molecular cloud collapses and fragments into individual protostars, the process is chaotic and hierarchical. Large fragments break into smaller ones, and smaller ones break into smaller ones still, through a cascade of gravitational instabilities. The smallest, most numerous fragments are the ones that produce the most stars. The larger fragments are rarer. The very largest, the ones that might produce stars like R136a1, are extraordinarily rare, requiring special conditions of density, gas supply, and cluster dynamics that only occur in the most extreme star-forming environments. This is why the Tarantula Nebula and the R136 cluster are so important. They represent one of the most extreme star-forming environments in the local group, possibly the most extreme currently active one, and the extraordinary density and gas richness of that environment pushed the upper end of the IMF to masses that would simply not be achieved in more typical star-forming regions. The Orion Nebula, which is the nearest star-forming region to Earth, and one of the most studied in the sky, contains hundreds of young stars. The most massive ones are in the range of perhaps 20 to 40 solar masses. That's it. The Orion Nebula, for all its beauty and scientific importance, doesn't come close to producing anything like R136a1. So R136a1 is rare not because something went wrong in our cosmic neighbourhood, but because the conditions required to produce it are themselves rare. The universe does make objects like this, but it makes them selectively in specific extreme environments at specific moments in the evolution of those environments. And because they live such short lives, the probability of one existing at any given moment in any given galaxy is very low. The Milky Way, despite containing hundreds of billions of stars, may not currently have a single star above 100 solar masses. The conditions for producing them simply haven't occurred recently enough in our galaxy's star-forming history. The Tarantula Nebula, by contrast, is producing an entire cluster of them simultaneously. It is a factory operating at a rate of production that is extraordinary by any standard, and R136a1 is its most extreme product. Chapter 16. The Chemical Legacy. How R136a1 built you. Here is something that I want you to sit with, because I think it's the most personally relevant thing in this entire video, and it tends to get lost in the avalanche of spectacular numbers and extreme physics. You're made of star stuff. Carl Sagan said it famously, and it's become something of a cliche in science communication, but cliches become cliches because they contain profound truths, and this one is worth unpacking in detail in the context of R136a1. because not all star stuff is equal. The atoms in your body came from specific types of stars, produced through specific nuclear processes, scattered across space through specific mechanisms. And massive stars like R136a1 are among the most important contributors to the chemical inventory of the universe, the periodic table of elements that everything, including you, is built from. Let's trace the chemistry. The hydrogen in your body, in your water, in your organic molecules, in your DNA, is primordial. It was produced in the first few minutes after the Big Bang during a period called Big Bang nucleosynthesis, when the universe was hot and dense enough for protons and neutrons to fuse together. The hydrogen in you is the oldest stuff in the universe, predating any stars by hundreds of millions of years. The helium in the universe is also mostly primordial, though stars produce more of it through hydrogen fusion. But from lithium upward on the periodic table, the story changes. These heavier elements, carbon, nitrogen, oxygen, neon, sodium, magnesium, silicon, phosphorus, sulfur, chlorine, potassium, calcium, iron, and everything else, were not produced in the Big Bang. They were produced inside stars and scattered into space when those stars died. This process is called stellar nucleosynthesis, and it is one of the most important processes in the history of the universe. Different elements are produced by different types of stars in different processes. Carbon and oxygen, elements absolutely central to life as we know it, are produced primarily in the cores of intermediate mass stars like the Sun through the triple alpha process during the helium burning phase, and then scattered into space when the star sheds its outer layers in a planetary nebula. But the most massive stars like R136a1, produce a far wider range of elements, and they produce them in far greater quantities per star. In the core of R136a1, nuclear fusion is currently proceeding through a sequence that starts with hydrogen and builds progressively heavier elements. Hydrogen fuses to helium. Helium fuses to carbon and oxygen. Carbon fuses to produce neon and magnesium. Neon burning produces oxygen and magnesium. Oxygen burning produces silicon, sulfur, and other elements around that mass range. And silicon burning, the final stage of core nuclear fusion before the iron peak, produces a cascade of elements near iron: chromium, manganese, iron, cobalt, nickel. Each of these burning stages is happening in nested shells around the star's core, like the layers of an onion. The innermost layer is the most advanced in nuclear burning, producing the heaviest elements. The outer layers are burning lighter fuels. The star is, at any given moment, a multi-layered nuclear chemistry experiment operating at temperatures of billions of degrees. When R136a1 dies, whether in a pair instability supernova or through some other mechanism, all of these elements get scattered into space. A single pair instability supernova can synthesize and eject several solar masses of oxygen, carbon, silicon, sulfur, and other elements. It can produce iron group elements in quantities that would take thousands of ordinary supernovae to match. The yield of heavy elements from a single pair instability supernova is extraordinary. And then there's the R process, the rapid neutron capture process, which is responsible for producing roughly half of all the elements heavier than iron in the universe. Elements like gold, platinum, uranium, thorium, iodine, barium, and many others cannot be produced through normal stellar fusion. They require an environment with an extraordinarily high flux of free neutrons, which allows atomic nuclei to capture neutrons faster than they can undergo radioactive decay, building up heavier and heavier nuclei in a rapid cascade. The astrophysical sites of the R process are still not completely pinned down. Neutron star mergers are the primary candidate, confirmed by the detection of gravitational waves and the subsequent observation of a kilonova in 2017. But certain types of extreme stellar explosions, including possibly some pair instability events in rapidly rotating stars, may also contribute. So when R136a1 eventually explodes, the material it ejects will mix with the surrounding gas in the Tarantula Nebula. That enriched gas, carrying the oxygen, carbon, silicon, iron, and other elements, synthesized in R136a1's core over its brief but intense lifetime, will eventually cool and condense. Parts of it will be incorporated into new molecular clouds. Those clouds will collapse, fragment, and form new stars. Around some of those new stars, the heavy elements in the cloud will condense into solid particles, forming the building blocks of rocky planets. On some of those rocky planets, The carbon chemistry that R136a1 helped supply might eventually organise itself into self-replicating molecules, and from there, billions of years of evolution might produce something that looks up at the night sky and wonders where it came from. The carbon in your body has a history. It was forged in stellar interiors, possibly including the interiors of stars very similar to R136a1, by stars that lived and died billions of years before the Sun was born. The iron in your hemoglobin was produced in the cores of massive stars and scattered by their supernovae across the interstellar medium of the early Milky Way. The calcium in your bones, the phosphorus in your DNA, the oxygen in the water that makes up most of your mass. All of it has a stellar provenance. All of it passed through at least one star, and likely several, before finding its way into you. You're not just observing R136a1 from a distance. You are, in a very real chemical sense, made of the same stuff that stars like R136a1 have been producing and distributing throughout the universe for its entire history. The connection between you and this extraordinary object 160,000 light-years away is not metaphorical. It is literally written in the atoms of your body. Chapter 17, The Cosmic Context, R136a1 in the story of the universe. Let's zoom out now to the largest scale I can manage, because I think R136a1 makes the most sense, has the deepest meaning, when you understand it not as an isolated curiosity, but as a character in the ongoing story of the universe. The universe began 13.8 billion years ago in the Big Bang. In the first few minutes, the basic building blocks were established: hydrogen, helium, and trace amounts of lithium. The universe expanded, cooled, and darkened as it entered what cosmologists call the cosmic dark ages, a period of perhaps several 100 million years during which there were no stars, no galaxies, no sources of light. Just an expanding sea of gas, slightly denser in some regions than others, due to quantum fluctuations in the very early universe, slowly being amplified by gravity. Then, somewhere between 100 and 400 million years after the Big Bang, the first stars ignited. Population 3 stars, composed almost entirely of hydrogen and helium, having no heavier elements at all, blazed to life in the densest regions of the primordial gas distribution. They were likely the most massive, most luminous, most extreme stars that have ever existed in the history of the universe. They burned briefly and violently, and when they died, they released the first heavy elements into the intergalactic medium. They also produced ionizing radiation that began heating and ionizing the surrounding neutral hydrogen. The beginning of the epoch of reionization, when the universe transitioned from a neutral, foggy state to the transparent, ionized medium we observe today. These population 3 stars are gone, every single one of them long since dead. They left behind black holes, heavy elements, and the chemical foundation for everything that followed. The second generation of stars, or population 2 stars, formed from gas that had been enriched by the deaths of population 3 stars. They had slightly higher metallicities, slightly stronger stellar winds, slightly different properties. They in turn lived and died, enriching the universe further, building up the inventory of heavy elements steadily over billions of years. The third generation, population 1 stars including our Sun, formed from gas enriched by all the previous generations. They have the highest metallicities, the richest chemical compositions, and they are the stars most likely to host planets with the right chemistry for life. R136a1 sits somewhere in this lineage, not a population 3 star, not as chemically enriched as the Sun, but somewhere in between. It formed in the Large Magellanic Cloud, which has lower metallicity than the Milky Way due to its different chemical evolution history, and it represents in some ways a bridge between the extreme early universe and the more chemically complex present. It is one of the most massive stars currently in existence in the universe, and it is burning with a ferocity that echoes the earliest, most extreme stellar populations. In the grand sweep of cosmic time, R136a1 occupies an instant. It will live for perhaps 3 to 5 million years total, possibly less, given its extraordinary mass loss rate. On the 13.8 billion year timeline of the universe, that is less than 0.04% of cosmic history. If you compressed the entire history of the universe into a single calendar year, R136a1's entire existence, from birth to death, would last about 3 hours, and yet in those 3 hours, it will produce more energy than the Sun will produce in its entire multi-billion-year existence. It will synthesize and eject more heavy elements than thousands of ordinary supernovae combined. It will shape the structure of the surrounding nebula, trigger new generations of star formation, and potentially leave behind a black hole that might, over billions of years, grow into one of the gravitational engines that organizes a galaxy. The brevity of its life is not a limitation. It is a concentration of impact into a small window of time, a burst of cosmic productivity so intense that it reverberates across scales and timescales far beyond itself. This is one of the deep patterns in the universe. The most extreme objects tend to have the shortest lives but the most far-reaching consequences. Population 3 stars lived for perhaps 1 million years and shaped the entire chemical and structural evolution of the universe for billions of years afterward. Massive stars like R136a1 live for a few million years and seed the surrounding medium with the heavy elements that make rocky planets and life possible. Gamma-ray bursts, some of the most energetic events in the universe, last for seconds or minutes and release more energy than the Sun will emit in its entire lifetime. Brief, violent, productive. The universe seems to have a preference for this kind of concentrated intensity at the high end of the energy spectrum. The most massive, most luminous, most short-lived objects are doing a disproportionate share of the work, producing elements, ionizing gas, triggering star formation, seeding black holes. They are the universe's most productive workers, and they are doing their jobs at a frantic pace before time runs out. Chapter 18. The Unanswered Questions. What we still don't know. I want to be honest with you about something, because I think honesty about what we don't know is just as important as enthusiasm about what we do know, and there is genuinely a lot we don't know about R136a1. The uncertainties are real, the open questions are significant, and acknowledging them doesn't diminish the wonder of the object. It enhances it, because it means the story isn't finished. The biggest open question is the precise mass. We've talked about this throughout the video, but I want to come back to it one more time because it matters enormously for the star's evolutionary fate. The difference between a current mass of 200 solar masses and 250 solar masses might seem relatively minor given the uncertainties, but it could be the difference between a pair instability supernova that completely destroys the star and a pulsational pair instability event followed by a direct collapse to a black hole. The death mechanism is exquisitely sensitive to the exact core mass at the time of collapse, and our current ability to predict the core mass for R136a1 is limited by both observational uncertainties in the current mass and theoretical uncertainties in the mass loss rates during its remaining lifetime. The mass loss question is itself deeply uncertain. Stellar winds from massive Wolf-Rayet stars are driven by radiation pressure on heavy elements in the atmosphere, and modelling those winds requires detailed knowledge of the temperature structure, density structure, and composition of the wind at every layer. The models have improved dramatically over the past few decades, but they still carry significant uncertainties, particularly for stars as extreme as R136a1, which pushes into regimes where the models haven't been calibrated against observations as thoroughly as would be ideal. If R136a1's mass loss rate is higher than our current best estimates, it will shed more mass before it dies, and might avoid the pair instability regime entirely, ending instead in a more conventional core collapse. If the rate is lower, the core might reach collapse with more mass and hit the pair instability regime squarely. Then there's the question of whether R136a1 formed as a single star, or through mergers of multiple massive stars. This question matters not just historically, not just for understanding how the star came to be, but for understanding its internal structure right now. A star that formed through one or more mergers might have a different chemical gradient, a different angular momentum distribution, a different magnetic field structure than a star that grew through standard accretion. These internal differences could affect how the star evolves, how it sheds mass, and ultimately how it dies. But we currently have no direct way to probe the internal structure of R136a1. We can only infer it from surface observations and theoretical models, and models of stellar mergers are still a relatively young and rapidly developing area of the field. The question of R136a1's multiplicity, whether it has close companions that haven't been resolved, is also genuinely open. At 160,000 light-years distance, two stars separated by even a few astronomical units would be completely unresolvable by any current instrument. Spectroscopic binaries, binary stars detected through the periodic Doppler shift of their spectral lines as the stars orbit each other, could in principle be identified, but the signal would be subtle and could be confused with variability in the stellar wind. Several searches have been conducted, and no conclusive evidence of a close companion has been found. But absence of evidence is not evidence of absence, especially when the observational challenges are this severe. There's also the fundamental question of what exactly a star at R136a1's luminosity looks like in terms of its atmospheric structure. The atmospheres of very luminous stars are so dominated by radiation pressure that they can be driven into a state called super-Eddington luminosity, where the luminosity locally exceeds the Eddington limit and the atmosphere is not in simple hydrostatic equilibrium. In this regime, the stellar surface can become highly structured and dynamic, with portions of the atmosphere being launched outward while others fall back, creating a complex turbulent zone rather than the relatively clean, stratified atmosphere of a lower luminosity star. Understanding this regime is important for correctly interpreting the observed spectra, and for accurately inferring the stellar properties from them. It's an active area of theoretical and computational research. And finally, there is the question of variability. R136a1 is not expected to be perfectly constant. Stars at this extreme mass and luminosity can undergo luminosity variations driven by internal pulsations, changes in the stellar wind, interactions with the radiation field and other mechanisms. Some massive stars exhibit what are called luminous blue variable eruptions, sudden dramatic increases in mass loss rate that last for years to decades and produce spectacular outbursts. Eta Carinae, which we mentioned earlier, is the most famous example. Could a 136a1 undergo something similar? Quite possibly, though its current Wolf-Rayet classification suggests it has already lost most of the hydrogen envelope that characterizes luminous blue variables, but the boundary between different classes of extreme massive stars is not sharp, and R136a1's behavior over the coming millennia, if we had the ability to observe it in that detail, might surprise us. Each of these open questions is a research program. Each one has people working on it right now, running simulations, analyzing archival data, designing new observations, arguing about interpretations at conferences, writing papers that will be argued about in return. The science of R136a1 is alive and ongoing, and the picture we have today, as detailed and as remarkable as it is, will continue to sharpen and evolve as tools and techniques improve. Chapter 19. The emotional weight of extreme science. I want to take a step back from the facts and figures for a moment and talk about something that I think doesn't get discussed enough in science communication. The emotional experience of learning about objects like R136a1. Because here's the thing, when I first really sat with the numbers, when I stopped just reading them off a page and actually tried to feel them, something strange happened. It wasn't just intellectual excitement, though that was certainly there. It was something closer to vertigo, a genuine, physical sensation of the ground dropping away beneath my feet, of my ordinary sense of scale and proportion suddenly becoming useless and needing to be rebuilt from scratch. I think this response, this vertigo, is actually the correct response. Not because discomfort is inherently valuable, but because objects like R136a1 are genuinely, legitimately beyond the scale at which human intuition operates. We evolved to navigate a world of rocks and trees and human-sized distances. We have no built-in cognitive apparatus for processing the reality of a star 250 times more massive than the Sun, burning 6 million times more brightly, at a distance of 160,000 light-years, in a nebula so large that it would cast shadows on Earth if it were nearby. These things don't fit neatly into the brain. They require the brain to stretch, to reach, to try new configurations of thought that don't come naturally. And I think that stretching, that effort, is one of the most valuable things that science asks of us. Not because it's comfortable, but because it's honest. The universe is not human-scaled. The universe is not designed to be intuitively comprehensible to creatures who evolved on one small planet around one ordinary star in one unremarkable corner of one typical galaxy. The universe is vast and strange and indifferent to our intuitions. And when we encounter an object like R136a1, an object that forces us to acknowledge just how far outside our ordinary experience the universe extends. We are in some sense confronting reality as it actually is rather than as our evolved intuitions have constructed it. There's something humbling in that, something that I find genuinely moving in the way that encountering something much larger and older and more powerful than yourself can be moving. Not frightening, or not only frightening, but also somehow liberating. Because if the universe contains things this extreme, this far beyond ordinary experience, then our ordinary problems, our ordinary anxieties, our ordinary concerns are revealed as what they actually are. Small, local, contingent things that matter enormously to us, but are embedded in a context of almost incomprehensible scale and grandeur. This doesn't mean our problems don't matter. Of course they do. But there's a perspective shift, available when you really absorb something like R136a1 that I find genuinely useful. A recalibration, a reminder of where you are and what you're part of. You're not just a person with problems and obligations and a to-do list. You're a temporary arrangement of atoms that were forged in stellar explosions, on a planet circling a middle-aged star, in a galaxy that is one of hundreds of billions, in a universe that has been running its extraordinary experiment for 13.8 billion years and has produced objects as spectacularly impossible seeming as R136a1. That's the context, and it's a magnificent one. Chapter 20. The future of R136a1 studies. What comes next? Let me come back to the science for this final chapter, because I think the future of R136a1 research is genuinely exciting and worth spending some time on. The story of this star is not finished. It's not even close to finished, either scientifically or literally. R136a1 itself still has a few million years of burning left in it, and the tools we'll have available to study it in the coming decades will transform what we know about it. The extremely large telescope, when it enters operations, currently projected for the late 2020s, will be genuinely transformative for studies of dense stellar clusters like R136. Its 39-meter primary mirror, combined with state-of-the-art adaptive optic systems, will deliver angular resolutions and light-collecting power that are simply not achievable with any current facility. For R136a1 specifically, this means the possibility of resolving even closer companions than currently possible, better spatial separation of R136a1's light from its immediate neighbours and higher signal-to-noise spectra that will allow more precise measurements of the stellar wind properties and chemical abundances. The ELT will also be equipped with instruments designed specifically for studies of massive stars, including spectrographs optimized for the ultraviolet and infrared wavelength ranges, where Wolf-Rayet stars emit much of their radiation, and where many of the diagnostic spectral features are found. The combination of spatial resolution and spectral quality that the ELT will deliver for objects in the Tarantula Nebula will be unprecedented, and the resulting improvements in our understanding of the most massive stars known are difficult to overstate. The James Webb Space Telescope is already contributing new data on the Tarantula Nebula. Webb's first released science images included a stunning view of 30 Doriadas, the Tarantula Nebula, that revealed structures in the gas and dust that had never been seen before, including the earlier stages of star formation deeply embedded in the nebula material. Webb's infrared capabilities allow it to peer through dust clouds that are opaque to optical telescopes, revealing young stellar objects and protostars that are completely invisible to Hubble. In the context of R136a1 specifically, Webb provides better constraints on the infrared luminosity of the star and its neighbours, which is important for correctly modelling the overall spectral energy distribution and inferring stellar parameters more precisely. Future space telescopes designed for ultraviolet observations, the UV range where massive hot stars emit much of their radiation and where many wind diagnostics are found, could also make significant contributions. Proposals for large ultraviolet space observatories have been discussed in the astronomical community for years, and if any of these facilities are eventually built, they could deliver ultraviolet spectroscopy of R136a1 with a quality that would dramatically improve our understanding of the star's wind structure and chemical composition. There's also the possibility of detecting R136a1's eventual death. When R136a1 finally explodes, in 1 to 5 million years by current estimates, it will be visible from Earth with the naked eye, and almost certainly detectable from Earth with primitive instruments even in the daytime. A pair instability supernova at 160,000 light-years would be among the brightest supernova ever observed from Earth. It would outshine every other star in the sky, possibly approaching the brightness of the full moon at peak. The flash of light would last for weeks or months, slowly fading as the expanding shell of ejected material cooled. It would be one of the most spectacular astronomical events in recorded human history. Of course, this is 1 to 5 million years from now, which means it's not something any of us need to put in our calendars. But it's worth noting that on cosmic timescales, the death of R136a1 is imminent. If you compress the history of the universe into a year, R136a1's remaining lifetime would be about 1 to 5 minutes. The star is, in the most literal possible sense, living on borrowed time. Every day that passes, it burns through fuel it cannot replace, sheds mass it cannot recover, and moves one step closer to the extraordinary finale that awaits it. There's something poignant about that, I think. Here is the most massive star in the known universe, this extraordinary, violent, magnificent object that shouldn't exist but does, and it is already in its final chapter. It is already old by its own standards, already past the halfway point of its brief existence. The Wolf-Rayet phase it's currently in is typically a last gasp phase for massive stars, the final stage before the end. R136a1 is in its last act, and we happen to be here to see it. In the 13.8 billion year history of the universe, in the roughly 100,000 year history of modern humans, in the roughly 400 year history of telescopic astronomy, we happen to exist at precisely the moment when R136a1 is alive and observable and close enough to study. That's a remarkable coincidence. Or maybe not a coincidence. Maybe just a reminder that the universe is always doing something extraordinary somewhere, and we will find it if we look. Conclusion: the biggest star and the smallest observer. So let's bring it home. R136a1, a star somewhere between 200 and 300 times the mass of the Sun, located 160,000 light-years away in the Tarantula Nebula of the Large Magellanic Cloud. The most massive star ever confirmed, discovered through decades of increasingly sophisticated observation, culminating in a landmark 2010 analysis combining Hubble Space Telescope data with ground-based adaptive optics. A Wolf-Rayet star already shedding thousands of Earth masses of material per year through its extraordinary stellar wind, 6 to 9 million times more luminous than the Sun, surface temperature of 46,000 Kelvin, radius 30 to 40 times the Sun's, large enough to swallow Mercury and approach Venus if placed at the centre of our solar system. Age: 1 to 2 million years. Remaining lifetime: 1 to 5 million years, give or take. Death: potentially the most violent stellar explosion in the universe, a pair instability supernova that destroys the star completely, leaving nothing behind but enriched gas and, possibly, the seed of a black hole. Those are the facts, and they are extraordinary facts. But I want to leave you with something beyond the facts, because I think the facts on their own are only part of what makes R136a1 remarkable. What makes R136a1 truly remarkable is what it represents in the larger story of the universe. It represents the universe's capacity for excess, for going beyond what seems necessary, what seems stable, what seems physically permissible, and producing something so extreme that it challenges our models and forces us to rebuild our understanding from the ground up. The universe did not need to make a star this massive. The physics allows for plenty of perfectly functional stars at much more modest masses. But the universe made R136a1 anyway, in the most extreme star-forming environment available, through processes that involved collisions and mergers and dynamics that our simpler models didn't fully account for. The universe, it seems, has a taste for the spectacular. R136a1 also represents the universe's remarkable coherence across scales. The same nuclear physics that powers a bomb here on Earth is happening in the core of R136a1 at a rate so extreme that it outshines the entire Milky Way in certain wavelength ranges. The same quantum mechanical principles that govern the behavior of electrons in atoms in your body govern the behavior of electrons in the plasma of R136a1's stellar wind. The same gravitational physics that keeps you on the surface of Earth is engaged in a billion-year war with radiation pressure in the interior of R136a1. The universe runs on one set of rules. Those rules play out in dramatically different ways depending on the conditions, but the underlying physics is the same, and that unity, that coherence from the subatomic to the cosmic, is one of the most beautiful things about the universe we live in. And finally, R136a1 represents the universe's generativity, its tendency to use extreme, violent processes to create the conditions for complexity, chemistry, and ultimately life. The heavy elements that R136a1 is synthesizing right now in its core will, billions of years from now, be incorporated into new stars, new planets, and possibly the biochemistry of living things that we cannot imagine. The violence of R136a1's death will be, in the long run, creative. The universe's most extreme star is, paradoxically, one of the universe's most productive contributors to the conditions that make life possible. You're sitting here, watching this video, thinking about R136a1, because the universe has been doing this, forging heavy elements in stellar cores and scattering them across the cosmos through spectacular explosions for 13.8 billion years. Every atom in your body is the product of that process. You're the universe looking at itself, using eyes made of star stuff to observe the most extreme star it currently contains. That's not a small thing, that's actually an extraordinary thing, and I think it's worth pausing just for a moment to feel the full weight of it. R136a1 is out there right now, 160,000 light-years away, blazing at 6 million solar luminosities, losing thousands of Earth masses of material every year, burning through its fuel at a rate that will exhaust it in the cosmic equivalent of an instant. It doesn't know we're watching, it doesn't care. It's just doing what the laws of physics compel it to do, playing out the inevitable consequence of having too much mass in the wrong, or the most gloriously right place at the right time. And we're here. Small, brief, improbable arrangements of atoms on a pale blue dot, with telescopes and mathematics and an insatiable curiosity about where we came from and what else is out there. And we found it. We looked at a smear of light 160,000 light-years away, in a dense cluster inside a turbulent nebula, and we resolved it into individual stars, and we analysed the light, and we figured out what it was. That's remarkable. Not just the star, the fact that we found it, the fact that we understood it, the fact that we could. If you enjoyed this video and you want more of this kind of deep dive into the universe's most extreme objects, make sure you subscribe, because we do this regularly here, and there are so many more extraordinary things to talk about. If this video gave you that feeling, that vertigo, that recalibration of scale, drop a comment below. I genuinely love reading those. It means the thing I was trying to do actually worked. Thank you for watching, take care of yourselves out there, and keep looking up.